So in this example, we're going to be determining if these two functions are even, odd, or neither. So I'm going to start with function 1 here on the left. If you look at it, you can see that if I draw a line straight down the middle, both sides look basically the same. It's a reflection across the y-axis there, which would make this an even function. And I can also highlight the graph and create a copy, and if I flip this copy, you can see even more that they're basically the same thing. They line up perfectly. If I could make it transparent, I would, but the graph is just a mirror image of itself. So that clarifies hopefully that it's even. And then for the one on the left here, if I were to do the same thing and take my graph, make a copy, and try to flip it here to see if it's even, we would notice that, well, it doesn't have the same shape now. It kind of looks like it's one's going down from left to right, and the general trend is going up. So it's not the same thing if I were to reflect it, which means it's not even. So if I reflect it back, now the test for odd is that it has rotational symmetry about the origin. So if I rotate this, not make it bigger, there we go. Rotate it 180 degrees, and hopefully I can get it pretty good there. So if I rotate 180 degrees, you can see that the shape is the same exact shape and located in the same exact position. It'd be nice if I could do a transparency with this. If I could, you would see that they line up perfectly. So because this graph is just rotated 180 degrees, spun all the way around, and would be in the same exact spot, this would be an odd function. Now, to determine if a function is even, odd, or neither from an equation, what we do is we plug in negative x. And then one of three things is going to happen. Let's start by plugging in negative x. So if I go and replace x with negative x, that's going to give me 4 times negative x to the 4th plus 1, or plus 5. To simplify this, I have to start by dealing with the exponents. If I raise negative x to the 4th power, essentially what we're doing, the coefficient with x would be negative 1, and we have x. Essentially, we have to raise both of those to the 4th power. Negative 1 to the 4th power is just 1, and x to the 4th power is just x to the 4th. So in other words, negative x in parentheses to the 4th power is just x to the 4th. 4 comes down, plus 5 comes down. And at this point, we can't simplify this any farther. So the first thing we want to check once we get it simplified is what we have right now. Is it the same as f of x? So is it the same thing as the original? And 4x to the 4th plus 5 is exactly the same thing as the original. Therefore, this is even. Okay, so first one is even. Second one, we're going to start off the same way to see if it's even. We're going to check even first. So we're going to replace x with negative x. So we have 2 times negative x to the 3rd plus 3 times negative x. If we do this, starting with the exponent, we have negative x in parentheses to the 3rd. So off to the side, that's the same thing as negative 1 to the 3rd times x to the 3rd. Negative 1 to the 3rd is still negative 1. X to the 3rd is x to the 3rd. So we would have 2 times negative x to the 3rd, if I simplify that. 2 times negative x to the 3rd is really just negative 2x to the 3rd. Cool, first term dealt with. Second term, we really just have the 3 times negative x, which is going to make it negative 3x. So now for the check for even, now that I've simplified g of negative x. So when I check to see if it's even, I want to see if this is the same thing as the original equation. So after replacing x with negative x, did it simplify to be the same thing as what we started with? Well, no. I can see that I have a negative 2 rather than a positive 2. So it is not even because it did not simplify to be the same exact expression. Next, we'll check for odd. The condition for it to be odd is that it is negative 1 times the original function. So let's go ahead and check to see if it's odd by factoring out a negative 1 from both terms. If I divide both terms by negative 1, I have 2x to the third plus 3x. So we have negative 1. Is this the original function g of x? Well, yes, it is. Therefore, this is odd. If it is even, after simplifying f of negative x, it will be the same thing as what we start with. However, if it's odd, it won't work out. Instead, we would have to pull out negative 1, and then we would see that it's negative 1 times the original function. If it is neither even nor odd, if you factor the negative 1 out and it's still not the original function, then it's simply just neither. And just as a reminder, if you have negative x in parentheses to an odd power, then it's the same thing as negative x to that same power. However, if it is negative x in parentheses to an even power, well, any number to an even power becomes a positive, so it would end up being just x to that same original exponent if the exponent's even. Okay, so in this is just a vocab thing dealing with the different types of polynomial functions that we're looking at during this unit. So there are higher power ones, but as far as transformations go, these are our focus. So we've already talked about quadratics in the past. Quadratics is x squared. Cubics is x to the third, with this general shape going up from left to right. And quartic is very similar to quadratic, except that u kind of bottoms out a little bit before going back up. It's not completely flat, but it gets very much stretched along the x-axis and a lot closer than what it is as a quadratic. Some key characteristics with these three: they all share the fact that they all go through the origin at 0, 0. And as far as graphing with transformations and stuff goes, each of them will always go to the right one, mixing out my left and right, and up one. They also go through 1, 1. All three of these go to the right one and up one. Right one and up one, going through 1, 1. The ones with even degrees are reflected across the x-axis, where the odd degree polynomial is not reflected across the x-axis, but rotated 180 degrees to get to -1, -1. In other words, the odd one goes left 1 and down 1 instead of left 1 and up 1 like the other two graphs do. Okay, in this example, we're going to be describing transformations. We've done this before. Just as a quick refresher, I usually use the rule that if it's inside parentheses, it affects the x values in the opposite way, while if it's outside, it affects the y values in the same way. In addition, for the transformations, addition and subtraction is a translation, while multiplication by a number that's not 1 creates a dilation. I'm not sure if I spelled that right. I can't spell dilation. And if it is, so that's multiplication. And if it's multiplication by a negative, it creates a reflection. So there we go. Those are the general things we've used with describing transformations before. So in this first one, this is a cubic because of the exponent of 3. As far as transformations go, there is 2 operations happening to the x to the third. The x to the third just tells us what type of function it is and doesn't actually tell transformations. So the operations, multiplication, addition, and subtraction, will tell us what transformations have happened to the graph of x to the third. So first, starting with multiplication, we have multiplying by 3. So that means we are dilating. And in this case, since it's a number bigger than 1, it is a stretch. If you want to be more specific, it's going to be a vertical stretch. Because it is outside parentheses, so it's going to affect the y values by a factor of 3. We also have addition and subtraction. So my minus 18, since it's addition and subtraction, is going to create a translation. So it's translated. And since it's outside, it's going to be affecting y values, so up and down. Since it's subtracting, it's going to affect it the same way since it's outside. So we're going to be subtracting 18, which is going to move the graph down by 18. And this is what's happening to the graph of x to the third. Of x to the third is blah, blah, blah. There we go. And for the one on the right here, this is also an x to the third graph. So starting off with that, the graph of x to the third is ... Okay, starting with multiplication, I do see multiplication. We have times 5. This is on the outside, so it's going to affect the y values. And since it's on the outside, we are going to be multiplying by 5 instead of dividing. So dilation, and I don't think there's an A. There we go. Dilation, it's stretch again because we're multiplying by 5. So dilation vertically. Oops, stretch. I meant to say stretch, but it is going to be vertical. It is vertical because it's outside the parentheses by a factor of 5. Next, addition and subtraction. So I do have addition and subtraction. I actually have addition and subtraction inside and outside this time. Both are going to create translations. So we are translating. So I'm going to start with the inside. Inside affects x, but in the opposite way. So I know it's going to be left and right. And normally if you're subtracting 2, you're going to expect it to move in the negative direction, which is left. However, inside affects the x values in the opposite way. So it's actually going to move to the right. So it can move right 2. And then we are also adding 4 on the outside. So outside affects the y values, but in the same way as what you would expect. So since we are adding 4 to y's, it's going to be moving up 4 units. And there we go. So in this example, we are given the graph of either a cubic third degree or quartic fourth degree function below. And we're going to use transformations to write the equation for the function. So starting off, in general, if we're writing an equation with transformations, it's going to have this general format. We might have a coefficient. We'll have x plus or minus something to a power, and then plus or minus something. Now the power is determined by the shape of the graph. This shape here is the cubic shape, so I know my exponent is going to be 3. Now the other spaces are for transformations, and we could technically have something right there, but polynomial functions could be rewritten so that you don't need to put a number there. So most of the time, you'll just write it without a coefficient beside x. However, there could be one. It's just not typically the case, just because it can be rewritten. Okay, so with that said, going through, I'm going to start by figuring out the translations. So normally it's centered right here. You can see that the center is now over there at -3, -1. So we've moved left 1, 2, 3. We went left 3. So we subtracted 3 from x values, which means the equation is going to place this inside, but in the opposite way. Since we subtract 3, it's really going to be adding 3 in the equation. Now for the y values, we actually go down 1 from where we start. So down 1, or -1 to the y values. And outside affects the y values. So we're going to place this 1 outside, and it affects the y values in the same way. So we're not going to change the operation there. We're just going to put -1. Lastly, we need to check for dilations and reflections. And normally with polynomial functions, we will go to the right one and up one. If it doesn't go to the right one and up one, then something is up with the dilations and or reflections. So instead, still go to the right one, but then we can just look up or down and see how far it's been stretched or reflected. Since it goes down 1 instead, we know that we multiply the original value by 1 to stretch it or reflect it in that negative direction. So I know that since it goes down 1 instead of up 1 like it should, this will be -1. It seems to behave like slope, but it's not the same thing. It does have a similar sort of fashion, but you're still always going over 1 regardless of how far up and down you actually do go, which is different from how slope actually behaves. It has a very similar feel though when we go to write it. Now for the second one over here, we have the same format. We're going to have f of x, or I'll use g of x, get a different letter going on here. So g of x equals, we're going to possibly need a coefficient. We won't need a number beside x in most cases, but we'll probably need a coefficient inside. We might need an exponent. We need an exponent. This one is quartic, so it does tell us it's either cubic or quartic. Since it's the U shape, just upside down, I know it's going to be a 4th degree, a quartic graph. And we'll probably need a number there for the translation. So let's go ahead and look at the translations first. It normally starts here. You can see it's been moved up 1, 2, 3, 4, 5. So we've gone up 5 units, which means we're adding 5 to the y values. Well, y is affected by the outside stuff, and in the same way, so since we are adding 5, we're going to keep that operation the same, putting it on the outside. Now for the inside stuff, well, translated, we actually have to move it 1 to the right, so right 1, which means we took x values and added 1, but x's are affected by the stuff inside, but in the opposite way. Since what we actually did is add 1, we're going to be subtracting 1 from the x values in the equation. And lastly, we need to see if there is a coefficient for dilations and reflections. Well, normally from that vertex, the graph will go to the right one and up one. If it doesn't go to the right one and up one, we need a number there. If I look, it appears to go down 1 instead. So once again, this number would be -1. If it went down 2, we would put -2 there. If it went up 7, we would put a 7 there. But that is it. There's our two equations for these two functions.